Hey, Calculus, Mr. Florio. This is going to be section 5.5, U-Substitution. Um, this is one of the first integration techniques that is pretty tricky. We've been following the power rule or trig antiderivatives and stuff, but this is the first one where we're going to do something kind of new. And it starts from going back to an old derivative rule that we had. If you ever had a composition of functions, and I asked you to take the derivative of a composition. The way we did that was we identified the outer function, took its derivative, left the inner function the same, and then just multiplied that by the derivative of the inner function. And that's what we call the chain rule, if that looks familiar. Um, so, for example, if I had something like x squared plus 4 to the 11th, and I said, let's take the derivative of that function. The outer function is something to the 11th. The derivative of something to the 11th is 11 times that something to the 10th. And we would leave the inside function alone and then multiply by the derivative of the inside function. The derivative of x squared plus 4 is just 2x. So the x squared plus 4 is like the g of x. The 2x is the g prime of x. And then the outer function is the something to the 11th. And we're just using that chain rule here, right? This is like the f prime of g of x times g prime of x. So what we're kind of going for now is working backwards from that. Say I asked you to take the antiderivative of a function, and say that function was something that looked like this. F prime of some function times the derivative of that some function. If I were to go backwards, the antiderivative of something that's set up like this is just going to be that f of g of x. And then maybe there's a constant, maybe not. That's not the important part right now. So the idea is, if I took this piece right here, the 11 times x squared plus 4 to the 10th times 2x, and I asked you to take the antiderivative of that, find the definite integral or indefinite integral of that with respect to x, it's just going to be what we started with, that x squared plus 4 to the 11th, that f of g of x, and maybe there's some constant. So the idea here is we're just going backwards from the chain rule, and the only method is recognizing that if I have a composition of functions where the inner function's derivative is hanging out somewhere, then I can apply this rule. And the only way to get the feel for it is just doing a couple of examples. So down here, I have 3 videos that I'm going to link in the description. Again, make sure to like, share, comment, and subscribe. It'd really help the channel. In fact, if I can get 100,000 viewers like this video, I'll even send another video next week. But let's just do some examples here together. And this is this U-substitution technique, and I'll explain where the U is coming from. But here you have to recognize that there's a function and a composition of functions, and the inner function has its derivative kind of hanging out here. So what am I talking about? I want to find the antiderivative of this. One method is just foiling it out, distributing the 2x and taking it piece by piece. But if this power was a bigger power, that's kind of unrealistic. So the x squared plus 2, that function itself, its derivative is 2x. And recognizing that, I can call this function down in here, the x squared plus 1, I'm just going to call that u. And I'm recognizing that its derivative, the derivative of u with respect to x, is 2x. Just multiply both sides by dx. I'll never do this step again. I'm just going to write 2x dx from now on. And the derivative of u is 2x dx. So the 2x dx and the x squared plus 1, I'm going to rewrite in terms of u. Because really what I have here is I have this scenario in the works right here. My inner function g of x is going to be this x squared plus 1. The derivative is 2x, and the outer function is something to the second power. So we just need to rewrite this as this right here is what I called u. So this right here is u. So it's going to be u to the second power. The 2x dx is what I'm calling du. So that's my du. If I take the antiderivative of that, it's just going to be 1/3 u to the third plus some constant. And just rewrite everything in terms of x. That's going to be 1/3 x squared plus 1 to the third power plus c. And that's because that's what we said, right? U is the same thing as x squared plus 1, so I just replaced u with the x squared plus 1 at the end. It seems kind of like I work some magic here, but if I go back to this problem and take the derivative of it, I should get back to where I started. So let's check it. If I take the derivative of 1/3 x squared plus 1 to the third plus c, the derivative of the c is 0. That's just a constant. And then the inner function, we have something to the third power. The derivative of that is going to be 3 times that function to the second power. And then we need to multiply by the derivative of the inner function. The derivative of x squared plus 1 is 2x. And the 3's cancel out, and we just get x squared plus 1 squared times 2x, which is exactly where we started from. So it checks out that we did it correctly. And again, the idea is recognize you have a function and its derivative all in one. And if I can just rewrite that function in terms of u, its derivative is right there. We're just going to substitute those values in, take the antiderivative. It's a little bit easier function to find the antiderivative of, and then plug our x back in. So another example, here I see 5e to the 5x. And the function the outer function I see is e, the inner function is 5x. And I recognize that if I'm going to call that inner function 5x, its derivative would just be 5 du, 5 dx. Right, I'm just going to go right to that dx. I'm just going to tag that on. And then I can substitute directly in. I have the integral of e to the 5x, which I'm calling u. The 5 dx is what du is. So I directly substituted everything into terms of u. The antiderivative of e to the u is still e to the u plus c. And now I'm going to rewrite u as 5x. So this would be e to the 5x plus some constant. Okay. And again, we could check it by taking its derivative. If I want to take the derivative of e to the 5x plus c, the derivative of the constant is just 0, and the derivative of e to the 5x, well, the outer function is e to something. The derivative of e to something is e to that same something, times the derivative of the inner function. The derivative of 5x is just 5, which is the same thing as 5e to the 5x, which is what we started with. So that's how we know we did it right. All right, so a couple more examples. Take a minute to copy them down. Here again, we have a function and we're looking to see if there's a function and that function's derivative somewhere inside. So here I see the inner function x squared plus 1, and then I just recognize that if I were to call that u, its derivative would be 2x. And I almost have it. I want it just to be x dx, not 2x dx. But we can just divide both sides by 2, and we'll have what we're looking for. So 1/2 du is the same thing as x dx. And now I could directly substitute x dx for 1/2 du. And I could substitute the x squared plus 1 for u. So I'm going to rewrite this integral as the integral. Remember, this is going to be now u to the second. And the x dx part, I'm going to rewrite as times 1/2 u. I'm going to put the 1/2 here and the du here. From this point, I'll just take our antiderivative. That's going to be u to the third over 3, 1/2 u to the third over 3, plus some constant, 2 times 3 is 6. So this is going to be 1/6 u to the third plus c. And I'm going to rewrite u again as x squared plus 1. Okay. And that's it. Again, we could check it. If I take the derivative of that function, the derivative of 1/6 x squared plus 1 to the third plus c, the derivative of the constant goes away. The outer function is something to the third, so it's going to be 3 times our function to the second power now, times the derivative of the inner function. The derivative of x squared plus 1 is just 2x. And let's see, 3 times 2 is 6, and the 6 over 6 cancel out. So this 3 times 2 is 6, divided by that 6 is going to cancel out, and I just get that x times x squared plus 1 squared, which, plus some constant. Well, there was no constant, that's, we don't have to worry about the constant anyways. Which is what we started with, which is good, right? The derivative of the constant went away. So we still get the same answer. Let's do another one. Here, the only option for u, right, because I have a composition of functions here. I have my f of g of x here. I have the square root function, and inside of the 2x minus 1 function. I'm going to try taking u to be 2x minus 1 and see what happens here. If I take u to be that inner function, the derivative of u would be 2 dx. And I just want dx. I don't want the 2 in there, so I'm just going to divide both sides by 2. And now I can substitute directly in for that dx. So now I'm replacing this with the u and the dx with 1/2 du. So I'm going to rewrite this integral as the square root of 2x minus 1 is really the square root of u. And I'm going to replace the dx with 1/2 du. So I'm going to put the du here. I'm just going to put the 1/2. I can factor the 1/2 out of the integral, or I could leave it in. It doesn't matter. I'll just put it right here. Before I integrate this, let me just rewrite this as 1/2 u to the 1/2, because the square root is the same thing as raising to the 1/2. So now the antiderivative is going to be simple. Just use the power rule. Just add 1 to the exponent. So it's going to be 1/2 u to the, 1/2 plus 1 is 3/2. Divided by 3/2. And remember, dividing by 3/2 is the same thing as by multiplying by 2/3. Plus some constant. So let's see, the 2's cancel out. So I'm going to get 1/3 u to the 3/2 plus c. And here I just want to rewrite u as 2x minus 1. Because that's what u is. And that's our answer. We could check it again by taking the antiderivative. Or excuse me, taking the derivative of that function. So if I were to check that, take the derivative of 1/3 times 2x minus 1 to the 3/2 plus c. The derivative of the c is going to be 0. And then the outer function, the derivative of something to the 3/2 is going to be 3/2 times that something to the 3/2 minus 1 is 1/2. Times the derivative of the inside, the derivative of 2x minus 1 is 2. So here the 3's cancel out, the 2's cancel out, and we're just going to get 2x minus 1 to the 1/2, which is the same thing as the square root of 2x minus 1, which is what we started with, so that's how we know we did it right. Okay? We'll definitely get more practice doing these. There's really no shortcut. It's just recognizing that you have a function and its derivative and just getting the feel for it. And it just takes a lot of practice. So this one's going to be a little tricky too, and we'll see how we can do it. So first, I'm going to figure out what our u is. If I call u 2x minus 1. By the way, before I keep going, when I see this function, I just know, looking at it, that this is going to be a really tough thing to take the antiderivative of, because there's two functions being multiplied together. There's a square root. There's a function inside of a function. We really only have the ability to take antiderivatives of functions like x to some power, like x to the 4th, x to the 5th, or sine, cosine. But when the functions get a little complicated, you need to have some different techniques. And that's where this technique is coming from. I guess when you look at it, it doesn't look like it's anything harder than anything we've done before, but it turns out it is. Anyway, so if I'm going to call that u, du is just going to be 2dx. And you might see here where the problem's coming. I have this in terms of u. I can rewrite dx as 1/2 du. So I can take care of that. But what can I put in for that x? And I do not want to have an integral of two different variables. So I want to rewrite x in terms of u. I'm going to use this equation right here. I'm going to rewrite this instead of as u equals 2x minus 1. If I add 1 to both sides, I'm going to get u plus 1 equals 2x. And then divide both sides by 2. And I'm going to get u plus 1 over 2 equals x. Now I can replace that x with this expression right here. It was, again, clever stuff that none of us would have thought of on our own, but after seeing it, now you know a method that could work. So the x I'm going to replace with u plus 1 over 2. So that's what x is. The square root of 2x minus 1 is really just the square root of u, because that's what u is. So u is just getting replaced there. And the dx, so that's this part right here. The dx part, I'm replacing with 1/2 e to the u. Or excuse me, 1/2 du, not e to the u. Before I do anything, this looks in fact more complicated than the last one, but I can clean this up, and it won't be too bad. First things first, a half times a half is a fourth, so I can take this fourth out. The u plus 1 is still here, and that u to the square root of u is the same thing as u to the 1/2. Okay, and maybe it doesn't look much better. I'm going to factor the 1/4 out of the integral just because it's a constant and I just want to get it out of there. Now this piece right here I can just distribute, and then we're going to be okay. So u times u to the 1/2. Remember, you add the exponents. 1 plus a half is 3/2. And then u times 1 is, u to the 1/2 times 1 is just u to the 1/2. And now this is something that we can manage. If I take the antiderivative of all this stuff now, leave the 1/4 alone. U to the 3/2, the antiderivative, that's going to be u to the 3/2 plus 1 is 5/2 times 2/5. So remember, dividing by 5/2 is the same thing as multiplying by 2/5. Plus u to the 3/2 divided by 3/2, but dividing by 3/2 again is the same thing as multiplying by 2/3. Plus some constant, and that constant doesn't matter. We just know it's there, or it could be there. And then we got to clean it up and put everything back in terms of x. So just multiply the 1/4 in real quick. 1/4 times 2/5 is going to be 2/20, which is the same thing as 1/10. U to the 5/2. And 1/4 times, 1/4 times 2/3. 1/4 times 2/3 is 2/12, which is just 1/6. U to the 3/2 plus some constant. And now just replace u. We know u from up here is still 2x minus 1. So down here and here, just replace u with the 2x minus 1. And that is it. Definitely not easy. We could still check it, of course, if I just wanted to take the derivative of this. We can. So the derivative of the constant is 0, so that's going to go away. And let's see. If I take the derivative of this first piece, 5/2 times 10 is going to be 5 over 20. Times 2x minus 1 to the, let's see, 5/2 minus 1 is 3/2. Times the derivative of the inside, which is 2x. Plus the 3/2 times 1/6, that's going to give me 3/12. 3/2 minus 1 is 1/2. The derivative of the 2x minus 1 is 2. And the derivative of 2x minus 1 is 2, not 2x. I missed that. So let's see. 5 over 20 is just 1/4. And this is 2x minus 1 to the 3/2 times 2. 3 over 12 is also 1/4, and this is 2x minus 1 to the 1/2 times 2. All right, we're getting closer here. Let's see. I can factor out the one. Let's see. They both have a 2 times a 4th, so that's just going to be a half. And that's going to give me 2x minus 1 to the 3/2. This is going to give me 2x minus 1 to the 1/2. And I'm just going to have the, we'll leave the 1/2 here, I guess. I can factor out the 1/2, 2x minus 1 to the 3/2. Excuse me, to the 1/2. That's the smallest exponent. And if I do that, then I still have a 2x minus 1 here. Plus this 2x minus 1 all got taken out, so there's just a 1 here. So we're going to get 1/2 times 2x minus 1. We're going to take the square root of that. And the 1 minus 1 cancel out, so I just get 2x. And the 2's cancel out. So I just get x times the square root of 2x minus 1, which is x times the square root of 2x minus 1, what we started off with here. Looks like taking the derivative was probably, checking it was almost just as much work as doing the derivative. Doing the antiderivative. But that's that one. We'll do one more example, and then I'll probably have you guys try these ones on your own and do the answers on a different video. So here, I have the sine squared of 3x times cosine of 3x. Take the antiderivative all with respect to x. Again, we're looking for a function inside of a function. The way it's written, it's hard to see. I'm just going to rewrite this first part, the sine of 3x squared, as the sine of 3x squared. These are the same thing, notationally. They're just different ways of writing it. Times cosine of 3x dx. This might make it a little bit easier to see that I'm going to call this inside piece u, and let's see what happens. The derivative of sine of 3x would be cosine of 3x times the derivative of 3x, which is 3. And that's close. I just want cosine of 3x dx. I don't want that extra 3 in there. Just divide both sides by 3, and I get 1/3 du equals cosine of 3x dx. And now I can substitute in. So sine of 3x is what I'm going to call u to the second. Cosine of 3x dx is just the 1/3 du. And take the antiderivative. U to the second, the antiderivative of that's going to be u to the third over 3. Don't forget times the 1/3, and of course plus a constant. So that's going to be 1/9 u to the third plus a constant, and that u is sine of 3x. And we could check that one too. This one won't be bad. Take the derivative of 1/9 sine of 3x cubed plus c. The derivative of the constant 0. 3 times the 9th is 3/9 sine of 3x times the derivative of sine of 3x, which is cosine of 3x times 3. There's like 2 chain rules there. The 3 times 3 is 9. The 9 will cancel out with that 9. And I'm going to get my, I forgot, if I subtract 1 from 3, I get 2. So I'm going to get a final answer of sine of 3x squared times cosine of 3x, which is good because that's where we started. Anyways, yeah, those are just some examples. We'll do more, and hopefully the more you see, the more you do, the more helpful it'll be, and we'll do some in class together. This idea of U-substitution, it works when the problem's set up where its function and its derivative are being multiplied to each other, and you just got to try to make it work. And if it doesn't work, maybe you try something else for U. So these are options that I've used for U. I picked sine of 3x. I picked 2x minus 1. Sometimes there's more than one option. Sometimes this isn't really a viable method. So it just comes from experience. Um, and yeah, so if you want to copy down these next few, um, these ones are just some basic ones that I want you to try on your own. See if you can get it. If not, that's fine. I'm going to try to do a video where I just put the answers to A, B, C, D, E, and F, as well as some definite integrals. The only thing that we'll do in the next section too is just when we actually have to use the fundamental theorem of calculus and plug in our upper and lower limits. It's not going to add much. This was definitely the heart of the U substitution. Anyways, thanks for listening. This was brought to you by Raid Shadow Legends. Download for free today.